So let's get to, there's another thing I wanted to mention. I didn't talk about this in the Cantor series lecture, but this is going to be an important example later. So there's something called Q ratio normality. And this is just kind of, there's actually a whole bunch of different definitions of normal numbers. I mentioned about Q normality and I mentioned about Q distribution normality, and we took a significant amount of time to actually develop this notion of Q normality. It was a little more complicated. And the difference, we're basically, we want to quantify. So we say that X is Q ratio normal if, and we're going to write this Rn of Q, for all natural numbers K, and for all, let's say, pairs B1, B2 of equal length, where limit of, let's say, minimum of Qn of B1 and Qn of B2 is equal to infinity. So remember, we're quantifying over only blocks that have an infinite expectation. Remember, this was our expected value that we defined to actually say which blocks we're quantifying over. We have the limit as n goes to infinity of n sub n q of b1 in x divided by qn of b1 divided by n sub n q of b2 in x divided by qn of b2. And that might just, I mean, kind of, in some cases, this is just really not that interesting. This is just going to be the same thing as base 10 normality, of course, in base 10. We note that when Qn is going to infinity at a slow growth rate, meaning something like log of n, then we can just ignore these two terms right here, right? So if we have something like Qn is about log n, then it's going to be something like just limit of n sub nq of b1 in x over n sub n q of b2 in x. So the basic idea here is saying that all blocks of the same length are essentially showing up the same as each other, but in a different wording. And so some of the earlier work I was doing was dealing actually not just with like Q normality, Q distribution normality, but then relations to Q ratio normality. And when I write down some of the theorems coming up, it's going to touch on how this relates. Clearly, this is a weaker condition than Q normality. Is it strictly weaker or not? It is. I think I wanted to prove this on a lecture 4 or whatever, or 3, I guess, but we didn't have time. But this is weaker. So we know that n of q, the set of q normal numbers, is a subset of Rn of q, and sometimes it's a strict subset, as it turns out. So we'll talk in a little bit. I just wanted to give that definition before I forgot. And so let's talk about some examples of numbers that are complete somewhere in the Borel hierarchy. And we'll try to get to some actual proofs, because I want to, the proof techniques are very important, and this is what I want to say could transfer over to, say, other areas of math, basically, is what was one of the goals here. So, so theorem, n of b, so this is a set of numbers, numbers normal in base b. In base b is pi 0, 3 complete. Okay. So this is kind of a first basic result. This is due to Key and Linton in 1994. Okay. And a lot of the techniques, I'll give a sketch of how to do actually kind of this, and also a much more general result that I have with Dominic Vietniak, Dylan Airy, and Steve Jackson. The proof techniques roughly can extend to many places. But that was an early result. That settled the question of Kekris. Kekris asked, is this the case? And I gave the homework question last time to show that the set of numbers normal in base B is a pi 0, 3 set. So that's easy. That's just a matter of you write out the quantifiers and count them. Showing completeness, we need to do something called wage reduction. We'll talk about that in a bit. But that's kind of an early result. Now, Remember, part of the reason for this notation is for pi 0 alpha sets. These are preserved under countable intersections, right? That's the reason we have the the pi for intersections, sigma for sum. Those are preserved under unions. So we can ask something about what about theorem? Let's say the intersection from b equals 2 to infinity of n sub n of b, n of b. So this is the set of absolutely normal numbers. These are this is a set of numbers normal in all bases. So I want to emphasize where this is a little delicate, because we know that each of these, they're not only just pi 0, 3 sets, they're pi 0, 3 complete sets. Okay. So the intersection, so easy, is the following. That intersection from b equals 2 to infinity of n of b is pi 0, 3. Right? That's just entirely trivial, right? But the problem is that when you intersect, it's just like with Hausdorff dimension, for example. You're not guaranteed that what you get is going to still have the same complexity or same size or whatever. Because if you had something like, what about the set of normal numbers in base b that are in the interval 0, 1, and then the set of normal numbers in base b that are in the interval 7, 8. You intersect these, you get the empty set. It's still the pi 0, 3 set, but it's not pi 0, 3 complete, right? So you could look at something like A is n of b intersect 0, 1, and B is n of b intersect 7, 8. Right? These are both in pi 0, 3. But A intersect B, of course, that's also going to be in pi 0, 3, but it's equal to the empty set. So this is where we need to be careful, because there may be some characterization of the set of numbers normal in all bases that's not just a pi 0, 3 characterization. So this is due to Boettcher and Slayman, that they showed that this is pi 0, 3 complete. This is pi 0, 3 complete. And I want to emphasize that these problems that deal with numbers like in multiple different bases at the same time can be very complicated, to put it mildly. So things like, producing examples even of numbers normal in all bases. So when you're moving around between these different bases, it's not something so simple as like if you're saying a countable intersection of sets of full measure is full measure, then we don't really even we don't care about anything except that those sets are full measure. You get this for free. Here, it's not going to be so simple. You care about what's happening in each of the bases, and it's quite complicated. And even more complicated than this, we also get, so this was in 2013, and then we also have Boettcher, Hyber, I think, was on this, and Slayman. Did they do this? I forget if he was on this or not. For sure, at least Boettcher and Slayman. This is in 2014. The union from B equals 2 to infinity of NB is, so maybe there's some interesting characterization. So it may be the case that you're normal in at least one base. I mentioned this last time. Maybe every irrational number could be normal in some base, right? So maybe pi, for example, okay, maybe we don't know, since pi is irrational, maybe we have a hard time figuring out which base it's normal in, but maybe it turns out it's normal in base Graham's number plus 5 or something like that. I mean, who knows? So it could be the case that a theorem like this is true, but it's not true. And a proof of that that's not the case is that they show that, a hard proof, I mean, you can do it easier. This is sigma 0, 4 complete. So we have these pi 0, 3 complete sets, and we're taking a countable intersection, so we kind of expect to jump up a level. We're not guaranteed of that, right? It could be the case when you intersect them, you may go down, right? So this is where I want to emphasize that this is, complexity in the Borel hierarchy is not a notion of largeness. When you do these operations, your complexity can go down. Right? You can union. Imagine if you have you could take pi 0, okay, like take the set of normal numbers in base B, right, n of b, and union it with its complement. Let's say n of b complement. Well, this is just going to be the real line, which is a delta 0, 1 set. So taking unions can make it drop down. So just be careful. That's where I want it, because there's a tendency sometimes to think of these as notions of largeness, and they are not. So these are, and this paper was, this was a very long and difficult paper. We're not going to go over anything that really happened there. But Veronica Betcher is she's a master of dealing with all these problems in different bases. So what else do you have? I want to show the problem that initially got me looking at this stuff. So I mentioned I was talking to some of you afterwards in terms of what got me going in different directions. And I mean, in all fairness, if I just saw all these things from the very beginning, I probably would have just figured it's not for me. I'm more interested in something more concrete. And it wasn't until like literally 1 month before I moved to Poland, I was talking to Steve Jackson, who's a well-known set theorist at the University of North Texas. So I was Mario Sherbansky's postdoc, and he deals more with fractals and dynamical systems. And so I hadn't really talked to Steve. I mean, Steve was a nice guy, but there was some stuff I was kind of curious about, and I talked to him about a month before I moved to Poland. And that led on to, now I guess 9 years of collaborations. It's too bad we didn't start talking earlier, but sometimes things happen like this. And they're very interested in non-Borel sets. So let's go back to a set that I asked about earlier. I'm going to call this n-perp of B. And this is the set, I didn't name it this earlier, but this is the set we've seen already. So this is going to be the set of all real numbers x, such that, let's say, x plus n of b is a subset of n of b. So in other words, it's a set of all real numbers that preserve normality under addition, and we proved, I believe it was in the second talk, so we proved that Q is a subset of n-perp of b. So anytime you add a rational number to a normal number in base b, you get a normal number back. So what about this entire set? So the problem here, let's actually kind of unpack this definition a little bit. Right, this is going to be equal to the set of all real numbers. Okay, no problems there. Such that for all y in n of b, x plus y is in n of b. And so the problem right here is this is an uncountable quantification. And right, so this is where this exercise that you may or may not have done on showing that the set of normal numbers is pi 0, 3, that approach does not work in this case, because here you get an upper bound that it's either an upper bound of being analytic or co-analytic. And I guess sigma, so that's I guess that would be an upper bound of being co-analytic, because it's a for all. So I guess, yeah, you can get an upper bound of being co-analytic. And so is this even a Borel set? Is this a Borel set? And so kind of the idea is, if it's not a Borel set, then I don't want to say that that means there's no characterizations or theorems, but in some sense it's much weaker, that you can't describe this set without using some sort of uncountable quantification. Whereas, like say the set of normal numbers, you only need countable quantifications. So, you have in your definition of limit for all epsilon greater than 0, okay, that looks like an uncountable quantification because it's over the reals, but you can just do it for all natural numbers n and take 1 over n for epsilon, and it's still fine. So, and there's actually a real kind of real-world consequence. I don't mean real-world in the sense of like really real-world, but in terms of working as a mathematician. So there were several people that published papers that gave examples of members of this set that weren't rational numbers, even some pretty good people. And if this is not a Borel set, this is something that makes sense to do, right? Because, it's like there's no real characterization. Well, here's a class of them. Here's something that's of interest. It turns out there was a paper in 1976 due to Rosie that somehow or another nobody noticed or remembered until 2016. So just kind of, did I tell this story earlier? I think I did, yeah. Yeah, so just to kind of say what happened was that this was in Jan Bajod's book on normal numbers. It's one I mentioned from the beginning, and there are tons of references there. Jan Bajod forgot about it because he has a gigantic book full of tons of very interesting stuff. And other people just seemed to somehow not notice. It was mentioned like in this notes part of the chapters. And so just kind of no one knew about this. And then in 2016, there was this big conference on normal numbers in Vienna that I attended, and I just kind of wouldn't stop annoying people telling them about this result, and then it just sort of got known. And so people stopped publishing these sorts of papers because then it was kind of spreading through as being known. But his characterization is actually a Borel characterization, and it's a bit complicated. I don't want to write it now. I can send a reference. But he had a Pi03 characterization. And his definition is quite complicated, or his description is quite complicated. It's related to entropy, and it's kind of an entropy zero. It's something I don't want to get into because we didn't talk about that. I can talk afterwards about it. But he had a Pi03 characterization, and that immediately tells you, okay, we have a Borel set. Is it Pi03 complete? Well, this is a paper. This is my first paper with Steve Jackson. So due to Airy, Jackson, and myself, we have this n perp of b is Pi03 complete. And there's actually several other things in there we did as well. By the way, this is also, I should remark, this is a zero Hausdorff dimension set. And this was a very, very hard paper to find. I forget how we eventually found it. Like it was like a one-page paper or something in some obscure place. And they did, I forget what they did. It wasn't anything really that complicated. And I don't even remember the author. I could find in the references in my papers, but it turns out that the Hausdorff dimension, whatever Hausdorff dimension is equal to 0. But anyways, this is a Pi03 complete set, so you need the lower bound is really what's going to be hard, and I'll give you guys a technique for the lower bound a little bit later. But this is something we're very interested in. If you have any potentially non-Borel sets, I would really like to hear, even if they're not related to normal numbers in some other places. That's very interesting. And this one turned out to be Borel, but we did find some others that were not Borel, actually.
Actually, it's very rough estimation.
You mean this co-analytic upper bounder?
How's the dimension of this?
Well, it's 0. Yeah, but it's. You mean what's the estimate? You mean that was done in the paper, or? So the Hausdorff dimension is exactly equal to 0.
If you assume arithmetic.
So we're talking about n perp b. This is a set of numbers that preserve normality under addition. So this has Hausdorff dimension 0. It's a very, very small set.
Until now, I'm not sure because I don't understand.
Okay. So do you understand the definition of this set?
No, I'm not sure about the result.
Okay. We can talk later about it. So, we have some other Hausdorff dimension results in this paper. There's one. There's some related sets I don't want to talk about just in the interest of time. Okay, so what about, I promised Cantor series that we would bring it back to that. So basically at this point, all that was really known is about set of numbers normal in base B. And then of course there was these very interesting results about absolutely normal numbers or numbers normal in at least one base. And what about other types of normality? So what about like continued fraction normality? You know, we talked about that. What about beta expansion normality? What about Cantor series normality? And some of this is still open. So there's another type of normality we didn't discuss. What about the following? What about the set of x? We're going to call this n of alpha. What about the set of x such that x times alpha to the n is uniformly distributed mod 1? So this is another very interesting thing, and I want to say this is not the same thing as, say, like a beta expansion, right? Because what's happening at every step, you're not modding by 1 every step. When we had a beta expansion, what we did is we multiplied by beta and then went mod 1, and then we multiplied by beta again and then go mod 1. And then we talk about being uniformly distributed with respect to this other measure. Here, this is something totally different. And I want to remark that actually even this is an open question. Is 3/2 to the n, is this a uniformly distributed sequence or not? You know, there's a lot of like very, very, very hard questions related to these types of sequences. And so actually it's an ongoing project. I'll say right now, let's say in preparation. So in preparation, this is Kaneko and myself. That n of alpha is pi 0, 3 complete if alpha is piezo. Probably it's true for any alpha, but a piezo number, do you guys know what a piezo number is? No? Okay, so this is, we're going to algebra here. So alpha greater than 1 is piezo if all of its Galois conjugates are inside the unit circle in the complex plane. I'll draw a picture. So remember, what we mean by Galois conjugates is you take alpha, you take the minimal polynomial of alpha, and then you look at what are all the other roots of that polynomial. Those are the Galois conjugates of alpha. And we want them all to be small. So like basically we have this unit circle. This is the, let's say absolute value of z is less than 1. And we have some alpha out here. And so an example would be something like alpha is the golden ratio. So in this case, if alpha is a golden ratio, then the one other Galois conjugate is going to be like over here within the unit circle. And I don't want to, this is a whole other lectures and stuff I don't want to get into, but there's a certain sort of way that piezo bases behave closely to integer bases. They're often the nicest ones to deal with. And there's something really nice that, so there's Hajime Kaneko, so he's in University of Tsukuba. So he's there's two people I'm working there with there on different projects, Shigeki Akiyama and then Hajime Kaneko. And they both happened to visit me in Poznan like really recently on separate trips. So it was really nice to talk, to discuss some things with them. And when I was in the bomb shelter, I was working on some, not with this paper, but with the other guy in Tsukuba. I was writing some stuff on that paper, so trying to make the best of that time. But anyways, we have this, and we actually have something more general than this, but it seems to be the case that this is true, because like I said, we haven't written it and we haven't gotten a peer review yet, but you know, it seems true. Open question, is this true for all alpha? So let's say question, open question. But if you solve this, please wait for me to submit this paper, and then like, you know, just to be polite, is this true for all alpha? I have no idea how to do it for all alpha. Yeah, for all alpha, no idea.
What is your combination?
That n of alpha is pi 0, 3 complete for all alpha greater than 1. I would be shocked if this were not true. But, it's natural, yeah. You know, is there some, so basically what this is coming down to, because like this is all going to just seem like, okay, we're proving some Borel hierarchy abstract thing, what does this actually say? Well, if we're saying that the set of normal numbers is pi 0, 3 complete, that's like saying basically that there isn't some other simple characterization, right? So is it, you know, maybe it's the case that when alpha is equal to zeta of 7, that the set of alpha normal numbers is just equal to the set of badly approximable numbers, something weird like that, okay? We'd never expect that to be true, but just for example. If we know that for all alpha, n of alpha is pi 0, 3 complete, then we can immediately say, no, there is no such characterization like that. Probably there's nothing we can do to actually simplify describing normal numbers. So a lot of this is like a matter of saying that there is no hidden theorem. And in practice, like, you know, this isn't just like an academic exercise, because in practice, this does happen, right? Think about this thing with this set of numbers right here. There was a hidden theorem. It turns out that nobody read this article in Acta Arithmetica for some reason, but it was there. And so if you know that, if you know that this is a non-Borel set, then there's no reason to look for the hidden theorem. But it is a Borel set, and it just happens that there was this theorem. Okay, so maybe there's some special characterization here, probably not, but this would be telling you in some precise way that there is not. Okay, what about Cantor series normal numbers? And let's see, where did I put that thing to erase? Does anybody see where probably somewhere really obvious that I put it? Just Does anybody see? Okay, maybe it's not so obvious.
On table.
Ah, that's why I didn't see it. Thank you, thank you. And I mentioned a story before that I was, my initial stuff I was working on was all these things with Cantor series expansions and normality and all this, and I don't work on that. I still work on that some, but I've only really just coming back to it now. But that was initially in my career, I was looking at relations between them. And so I always wanted to prove some sort of like really good, satisfying independence results, like, are these notions really, really independent? And, I have a paper with Dylan Airy where we computed the Hausdorff dimension of the different sets and comes out at being 1 under some reasonable conditions. It can be empty, right? Because maybe the sets are just equal. Maybe normal and ratio are the same thing. But with Airy, Jackson, and myself, and this was published, I guess 2022 maybe, I forget when. I think we finished it in 2020. So this is in Journal Symbolic Logic. So we have a couple results. So the sets for all Q, dn of Q is pi03 completes. And let's say if, and then say for all Q, where the sum of 1 over Qn equals infinity, n of Q and dn of Q are pi03 completes. And if we have that the sum of 1 over Qn is finite, then we have these are just equal to the set of real numbers, which is Clopin. So we discussed kind of how if the bases are growing too quickly, then it's really, these sets aren't really something you want to care about too much. It's boring. So these notions are only interesting if, say in the case where your bases go to infinity, where they don't go too fast, or maybe your bases don't go to infinity at all, and it's still interesting. The hardest, let me actually just say that the hardest part, and there's another thing with difference hierarchy, this was really, really, really hard. So it wasn't difficult really at all to show that the set of distribution normal numbers was pi03 complete, but actually like working out all the details, just purely, not from an abstraction point of view, but purely from a problem solving standpoint, dealing with this was nasty. We also have, and this was the whole reason for the paper to begin with, all non-trivial different sets are D2 pi03 completes. And this is where things, I think, get a bit interesting. So I talked a little bit about the relationships between these sets, and this is also provided that Qn goes to infinity and sum of 1 over Qn is infinity. So this is only looking at this special case. There may be other cases where the different sets are non-empty, but I don't understand what's going on. So that'll actually lead me to from my perspective, one of the open questions I'm most interested in. So I'll just write it right now. So I'll say open question. So this is open. Is the set of Q such that n of Q equals dn of Q rel? So what this kind of comes down to, and let me just say like the philosophy behind why this open question is to appear in a paper with myself and Sohail Farhangi and maybe other co-authors. We're not sure. It depends who can help us with some things or not. But where we found, or rather, he did a lot of the dynamics behind here. If you look at Q itself being like a normal number or being like some sort of zero entropy sequence, then you have some interesting relationships between these sets of normal numbers. And it turns out when you have a zero entropy dynamically generated basic sequence, for example, something like the Thuy-Morse sequence, then normal equals distribution normal. And so the part of the motivation is we want to ask for which basic sequences should one generalize results in normal numbers to. So we can stay in base B and say, okay, this works for all B area expansions, but how far can you push those theorems? And we don't know if we just have a bunch of isolated islands of examples, which could be the case if this is not Borel, or maybe there's just some nice full characterization. And so that's something I'm very, very, very interested. So if anyone has any ideas what to do there, I suspect it's probably difficult. And there's some other similar questions like this. I didn't talk about the hotspot lemma, so I'm not going to write it, but these types of questions I'm very, very interested in right now, but I have no idea what to do. So here, this is a case where the theory of normal numbers behaves very differently, like I talked about in the Cantor series lecture. And so, for example, we have that, it turns out this set of ratio normal numbers that are not normal is D2 pi 0 3 complete. Okay. And why is that interesting? So, I mean, I already know actually that this is a set of full Hausdorff dimension. You can look up, there's a paper I have with Dylan Airy in Journal of Fractal Geometry where we prove that. But what does this tell us? So what are our consequences of this? So let's suppose that I wanted a theorem. Let's say we want condition, let's say P of x. So condition P of x, where let's say Rn of Q and P of x is, say, x in Rn of Q, and P of x is equivalent to x in n of Q, for example. So in other words, we want to say, okay, if you have a ratio normal number, and you want to tack on an additional condition, and make that being equivalent to being a normal number. So maybe there's some additional thing you can add on. Maybe there's a theorem like this. It turns out that if such a statement is true, and you can do this by tracing through all the definitions in the Borel hierarchy. If such a statement is true, then P of x is not a sigma 0 3 condition. Okay. Now keep in mind that sigma 0 3, this is also containing pi 0 2, sigma 0 2, pi 0 1, sigma 0 1. So for example, like let's suppose that I had a theorem. Like let's suppose that I think that if you're ratio normal and also badly approximable, maybe this gives you some more information. Maybe there's some weird things you can do to cook up numbers that are ratio normal but not normal, and being badly approximable blocks those things. Maybe that's the only obstruction, something having to do with some approximations. Well, it turns out that being badly approximable is at the second level. It's either pi 0 2 or sigma 0 2, I forget which. So that theorem is false, just based on the number of quantifiers you're using. So this is something kind of odd and different. So this is where it starts to become a little bit more like saying something exists by intersecting sets of full measure. But instead, we're dealing with like the number of quantifiers. So another thing that would be false, being ratio normal and essentially non-normal in base 37 is equivalent to being distribution normal. So condition like being essentially non-normal where the digit frequencies don't exist, this is a sigma 0 3 condition. So such a theorem is false as well. So for example, you say if Q is given by log of n, then you know without even constructing it that there exists a number that, for example, is ratio normal in base Q and badly approximable, essentially non-normal in base 37, that's not normal in base, say, log n. How would you construct something like this? I have absolutely no idea. But it doesn't matter because this condition of being badly approximable has too few alternating quantifiers. Sorry, not badly approximable, essentially non-normal. But it's true for badly approximable as well. Basically, any sigma 0 3 condition. So what's going on then is it's saying, okay, well, if you want a theorem like this, this condition P of x needs to be at least as complicated as the thing you're trying to get to. So essentially, they're independent because if you're trying to tack on an additional condition, it's it has to be a complicated condition. It can't just be some simple extra thing. Does that make sense and part of the motivation? So to me, this is like, if you only take away one thing from the series of lectures, looking at the Borel difference hierarchy, I think is a notion that needs far, far, far more attention. And I think especially people in dynamics and fractal geometry who can understand this idea of, looking at different sets and how Stork dimension of these, what it's going to say and all that. I think that this is an additional condition that also deserves attention. I think we should still compute Hausdorff dimensions of different sets, but I think we should additionally as well look at this too.
Just provocative question. I'm sure, more than sure, different variants in more than general law of strong large numbers. As a generalization of these theorems, you have a lot of ergodic theorems.
Yes, yes.
And you have a lot of different methods how to define normal numbers.
Yep.
All of these sets will go full Lebesgue measure.
Yep.
Let us intersect all of this definition. Would you prefer new definition of normal number?
So when you intersect all of these, it's uncountably many, and you get an empty set.
Maybe. Known theorems.
Well, so the thing is, there's uncountably many beta expansions. There's no real number that's normal for all beta expansions.
But actually, having B from natural number, because of course, if you consider Q expansion, you have continuous many, but they are still in normal. Beta is normal. Any blocks?
You could quantify over piezo beta, and people have, for example, given just natural numbers, so subsetting. Okay. So the set of, I guess we could say like Laroth series normal and continued fraction normal and absolutely normal and continued fraction normal. So that's, like I said, the thing. You can keep doing this. You get a non-empty set, but some of these classes are uncountable because if you go to generalized GLS, there's uncountably many, and it's. But what's the question exactly?
Of course, if you consider continuing many, but below MA expansion, and just not Marino-Lupin expansion, but it's generalized LNS expansion. You have a series of intervals with empty intersection whose union is almost empty interval. That is why sum of their lengths is sum of 1. But actually
Can maybe we can talk about it. Maybe if you formulate it precisely.
If you consider the 0, 1 minus this sum, it can be of 0 dimension set.
So for general,
so actually you have a set of intervals, but you know how these intervals is replaced. The sum of their lengths is sum of 1. But let us consider the difference. Interval 0, 1 minus unit of this interval. Y is, it can be that this difference is a full Hausdorff dimension.
Right, yeah.
Not just 1 point. What we can say in this case?
You mean about the
all this construction will destroy it in the sense of fractal geometry. Because of your counterexample will be a full Hausdorff dimension.
Let's talk a little more later because there's a lot. We only have 15 minutes left, and I can maybe answer after. Is that okay? Because there's still a lot more I want to talk about. And then maybe right after the. But So we'll talk about that in a little bit. But I want to I might as well right now just move over to about when we look at the different numeration systems. Maybe this will be relevant to your question. If we look at, so we want to include things like Laurent series, we want to include continued fractions and things like this. And we absolutely do not have time to state this theorem at all, but this is due to Airy, Jackson, Kvyatniak, and myself, and this is in 2020. So maybe this is relevant to something you were asking about. Many is we have a very general theorem where all, let's say, dynamical defined sets of normal numbers are pi03 completes. And I want to throw in a buzzword for those of you. We need something called the specification property. So there's something called the specification property that allows us to, we have actually something weaker than the specification. We call it actually the right feeble specification property. This is Dominic Kvyatniak is an expert on specification property, but basically let's say that all measure-preserving systems where we have some weak version of specification property, we don't require the space to be compact. We want to be able to deal with continued fractions. So we have continued fractions, we have like a, n to the n, right, is our digit space. This is not compact. So a lot of like normal theorems from dynamics we couldn't use here, so we needed two invariant measures. We needed two shift invariant measures that were different. And provided you have these technical conditions I'm not writing now just due to interest of time, and a way to almost concatenate blocks of digits, you get that the individual sets of normal numbers are pi03 complete. If you intersect them, well, we have no idea. And that could be very hard. But at least the individual ones are. So in particular, we get all beta expansions. So remember, we had this issue with beta expansions in lecture number 4, where, like, say, if beta is a golden ratio, we can't, if we have, we can't have two ones in a row. So, for example, if you want to concatenate these blocks, then you run into some problems, right? Normally, we don't have any issues with concatenation. And there's something called this, there's different levels of something called the specification property that can let you do something almost like a concatenation and still have a valid word. So in this particular example, anytime you concatenate, if you pad with a 0 in between, you can still concatenate. And it turns out not all beta expansions have that property. You need something a bit weaker to take everything on. But we have a condition that's sufficiently general to include all beta expansions. We also have continued fraction expansions, Laurent, in fact, generalized GLS as well. So a particular case of this, I mentioned this problem of Sharkovsky and Sivak. They asked, no matter which invariant measure you put on the tent map, where you have a tent map, you have a transformation like this.
Actually, 10 maps continuous 10 map for the individual.
It is.
As such as Sharkovsky said, in general, for multi-dimensional case, it's not true.
Yeah. This problem doesn't deal with multi-dimensional case. All they asked was basically in non-descriptive set theoretic words. So they had a question that was a descriptive set theory question, but they maybe didn't know how to formulate it in the way that set theorists do. They basically asked...
Maybe you will have a time, some of our guests, in 2 weeks, at the 5th of June, with a special sitting of Academy of Science of dedicated to academician Berezanski, not Sharkovsky, Berezanski, who actually survived this German theorem before defense of Sharkovsky. It's a special, you will have a possibility to obtain special information about how this theorem of Sharkovsky was survived.
Okay, yeah, I'm curious to hear. Let's talk in a little later. I'm curious to hear. When the 5th I'll have time, but then on the 6th and 7th I'm going to be teaching all day. So they asked if for every invariant measure on the tent map, it's the set of generic points or normal numbers is going to be pi 0, 3 hard. It's very easy to show it's pi 0, 3. So this was, I have no idea how Dominic actually even found this, but apparently he was able to find this question somewhere they asked, and so it was just a special case of this very general theorem. And I don't know that, I mean, I'm kind of, I would like to go a little bit over so I can give some proof techniques. I wanted to mention another interesting one that's due to Van de Heij, Jackson, and myself. So there's definitely no chance to describe the proof technique here due to Jackson, myself, and Van de Heij. And this is, let's say, accepted at Advances in Math. So this is on arXiv as of 2021, but it's let's say to appear in Advances in Math, and who knows when. So without generalized Riemann hypothesis. So remember that Van de Heij had this result where he showed that there are numbers that are continued fraction normal, but normal and no base, and he needed the generalized Riemann hypothesis. So we got rid of that using techniques from descriptive set theory that hopefully have a little time to describe. And we proved something, I think, more interesting, far more interesting. So we have theorem is that, let's say, normal continued fraction minus union base. So the set of numbers that are continued fraction normal, but not normal in any base. So remember, this is something that the difficulty was showing that this was even non-empty. Also, what's the Hausdorff dimension? No idea. Maybe 1, as you thought, who knows?
You secondly mentioned this problem.
Yeah, I mentioned it before. I'm mentioning it again, though, because it's interesting.
Actually, you already mentioned.
Yeah.
Having in mind generalized Riemann hypothesis, this is uncountable set.
Yes. Yeah. We talked about it.
I mentioned that more or less trivially, that is, if you obtain at least 1 point from the set.
Non-emptiness is the difficulty. What's the Hausdorff dimension? No idea. But what we proved...
It's trivially of full Hausdorff dimension.
Trivially, even if...
Yes.
Okay, let's talk later, because I don't see how...
Since it's trivially, it's trivially. Just a joke.
Oh, okay. I wasn't sure. Maybe there's something you knew that I didn't. That can happen. The theorem is D2 pi 0 3 hard. We don't have D2 pi 0 3 completeness. There's some finer hierarchies. We don't know exactly where this is. But in particular, a corollary of that is that it's non-empty. And we know that NCF also minus N of B is D2 pi 0 3 complete. So that's also something of interest. And here's, let's say, open question. It may be very, very hard. What about N of B minus NCF? So this set of numbers normal in base B that are not continued fraction normal. So it looks kind of like this, right? You just flip the direction, but this may be very, 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 very hard because I haven't gone over the proof techniques yet, but what you kind of need to do is you need to start with some example of one of these types of numbers and be able to kind of play around with it and perturb it and do some games with it. And what's a number that's normal in base B but not continued fraction normal? Well, there is something called Stoneham numbers, but they're not something you can really perturb around with. It's just some infinite series. A potential example would be something like the golden ratio, right? So we think that all algebraic irrational numbers are normal on all bases. This is the Borel conjecture. Let's say it's like the current big question involving normal numbers. But nobody knows this. This is currently quite out of reach. So, but a quadratic irrational, it's not continued fraction normal, right? It has a very boring continued fraction expansion.
Sure.
So proving something like this, it turns out it actually might be harder than the Borel conjecture. We don't know, I'm not sure about that, but at least our initial thoughts about it, it could be very, 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 very hard. So, and in fact, it was already enough, like I said, to get this published in a decent journal just to get one of the directions and not the other. That was already 40-some pages of hard continued fraction estimates. So please don't, read the intro to this paper, but please don't really get into the details unless you really like that type of thing. Interesting also is that and I don't want to say corollary, I don't know what the right word is, some result that follows by using the lemmas for the other results, but doesn't follow from the results. Maybe there's some name for that, I forget. Let's say not corollary, but almost. If, let's say, P and Q are relatively prime, then n of P minus n of Q is D2 pi 0 3 complete. And this is, also completely new result. We know that the Hausdorff dimension is going to be 1. This is known for 60 years at least, maybe more. I know Lee Schmidt had something like this. This is, so let's say open question, but probably not that hard. I think it'll be hard, but not too hard. Open question. What if log P over log Q is irrational? So almost surely that's going to be the actual right theorem, because the thing is, this theorem we got, it was just a matter of like theorem hopping with the lemmas that we used to prove this. So we didn't intend to prove this. We intended to do that as a separate project, but we just kind of got this for free in this special case where we have relatively prime bases. Is it true in the case that the ratio of their, if they're independent bases? For sure it is. If someone wants to dig into that, let me know. Maybe it's something to give a PhD student if they can understand this paper. I don't know that I'm going to work on it, but just so you know, that's a question. Give it a try. Let me see where we are in time, because I would really love to give a proof sketch. Is it okay if we go 15 minutes over or not? Okay, all right. So, how do we actually prove one of these results? So let me give a sketch of the proof of this theorem over here that I didn't fully state. Basically, when we can do like almost a concatenation, then we get pi 0 3 completeness. And so there's a technique, there's something called wage reduction. So what we need to do is we want to get outside of the descriptive set theory realm, because none of us here are descriptive set theorists, unless maybe someone is and didn't tell me yet. And I'd rather just deal with normal numbers, right? Probably most of you would rather deal with something else. So if you have a problem in some other area of math where you're dealing with something with Borel hierarchy, you want to move it to your area of math that you're more comfortable with. And so I can talk about the general statement of wage reduction later, but I'll say how we do this in particular with this problem. So it turns out the set of sequences, so let's say that you're in n to the n. This is the bare space, the set of integer sequences, and we can put the discrete topology and then take the product topology on this, and this is a Polish space. So in this space, the set of sequences xn, such that xn goes to infinity, is pi 0 3 complete. In this space with this topology, okay? And so what we need to do is the following. So let's say that we're just going to do this, let's say, with a set of numbers normal. In fact, I'll just make it easier. Numbers normal and base b. The technique generalizes, I'll say there. So let's say we want to show that n of b is pi 0 3. We want to show n of b is pi 0 3 hard. So what we need to do is we need to come up, so we need a continuous function let's say f that maps n to the n to r, where if, let's say, x, let's call this s right here. If x is an s, then f of x is normal in base B, and if x is not a member of S, then f of x is not normal in base B. So I'm not stating fully what wedge reduction is, but this is basically a special case, what it turns out to be. So we've kind of turned this into somewhat more of a combinatorial problem where if you give me a sequence of integers that goes to infinity, then my algorithm that works continuously on this sequence of integers should output a normal number. And if you're given a sequence of integers which does not go to infinity, then the output should be a number which is not normal. And if you can come up with a continuous function that does this, then you get that this set of normal numbers is pi 0, 3 hard. And there's going to always be some sort of connection like this. So this is what I'm saying. We turn it into this problem. It's a problem in normal numbers and not a problem in set theory anymore. And how do you do this? So, and I'm going to do this in such a way that you could imagine how you could generalize this to beta expansions or continued fraction expansions or whatever else. So we let, let's say, alpha be normal, and let's say beta be, let's say like 1/3, 2/3 normal. Let's say, well, we're in base B, let's say 1 over B minus epsilon, 1 over B plus epsilon, 1 over B, and so on, 1 over B normal. So what I mean by this is you weight the digit 0 with frequency 1 over B minus epsilon, weight the digit 1 with frequency 1 over B plus epsilon, and then just weight them all the same. And then what's going to be the frequency of 0, 1? It's this times this, and so on. So we have a number that's normal and a number that's normal, let's say, with respect to a different weighting or with respect to a different measure. So we have these two numbers, and what we do is the following. We consider, so we're given x, which is a sequence of integers, and we look at these, I'm going to look at a big block of digits here, and then a really, really much bigger block of digits b2, and then let's say a much, much, much bigger block of digits b3, and we're going to have the property that something like the length of bn is something like, I don't know, 2 to the 2 to the 2 to the n, whatever. Something that grows really, really, really quickly. The point is that we want some block of digits that completely dominates everything that happened before, so all that really matters when you're considering points in here, after some point, is just what's happening here. Well, we're getting there. There's still more to do. So what we need then is the following. So here's how we define some block of digits Cn is going to be given by the following. We start with, let's say this is some portion of 1 minus 1 over xn and 1 over xn. So we're given some member of our sequence xn, and the last 1 over xn of it, we put in digits from beta, and here we put in digits from alpha. We're always starting from the beginning. So for example, if xn was 10, then the last 1/10 is going to be digits from beta, and then the first 9/10 are digits from alpha. And we also need Cn to be much smaller than Bn minus 1. And then what we're going to do is, in Bn, we're going to have, let's say, Cn, many, 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 many times. The details of this are worked out in the paper. So this was published in Transactions of AMS in 2020. You can find it also on arXiv. The details get really complicated, but roughly what you're doing is you're putting down many, many copies of the same block. And there's an important reason why we do that. Because we want, let's suppose that xn is going to infinity. What happens? We want to output a normal number this way. So what's happening here is these blocks Cn, if xn is going to infinity, this portion from this bad number that's not normal is going to 0. So these blocks Cn should be looking more like there's a uniform distribution on the digits. So we can put these, we have many, many copies of here, and we could have a problem that like this block Cn, if this block is really, really big, then we could have some issue with the limits not existing, because if like the length of Cn was much bigger than the previous one, then we could have some oscillation in the limit, and we don't want that. We want a normal number. Does everyone see what the potential problem could be if we don't control the length right here? So that's very, very important, otherwise the whole thing falls apart. So what we end up getting is, so when we just put like a bunch of tons and tons of little copies.
So, but actually, if you consider counter series expansion, I can introduce counter series expansion for a given subsequent 2 power 2 power 2 power 2, then the limit will be exist.
That the what exists?
The limit can be exist. I will produce you a special counter expansion. So for
well, so remember, we're not dealing with counter series expansions here. We're dealing, so that's a whole different question, and it's actually much harder. So just we're dealing with things like, this is just base 10 expansion right here, base B expansion. So counter series, yeah, I can show you what happens in that paper. It's much, much, much worse and much more difficult. This is more abstract, the statement of the theorem, but the counter series one is much harder from a problem solving standpoint. So anyways, we get a normal number. If xn is going to infinity, then you can see that basically the distribution of the digits you can show precisely is converging to what you'd expect it to be for base B. Now let's say that xn does not go to infinity. Okay. So if xn is not going to infinity, well, that means that there is going to exist some number n, or no, maybe no, some number m, where xn is equal to m infinitely often. So what that means then is you look at that subsequence of these long blocks, and at the end of those long blocks, you're going to have a distribution that's, this overwhelms everything that happened before it. And you have one of two things. Either you have a distribution that's different from this uniform distribution you get in base B. So maybe the frequency of the digit 0 is something looking something like 1 over b minus epsilon. So that means your number is not normal if the limit exists, but then maybe the limit doesn't exist, because if xn is not equal to this number m after some point, then you're going to get an oscillation instead. So you have one of two things happening. Either you have an oscillation in the frequencies, so if it changes from m to something else infinitely often, then when you sample on these different points, you're getting something more similar to an essentially non-normal number. Or you just get some number where the frequencies are not what they're supposed to be. Either way, you break normality in this sense. Okay. And that's a bit of a sketch here in terms of how would you extend this result to a beta expansion. While we're doing this concatenation here, there's some weaker version of this thing called specification property, where this right feeble specification property that we called it, where you can do some padding in an almost insignificant way. And for this, you have to actually be allowed to change some of the initial digits here, but we can do it in such a way that it doesn't really affect the frequencies significantly after a point. These are some kind of very detailed analyses that are in the paper. Like, I don't want to get into really anything too precise on it now, but that's roughly the idea. So there's many concatenations. You have to do some sort of padding and changes. If you have a continued fraction expansion, you have infinitely many digits. Not a problem. You can take two different measures. There's you can take the Minkowski one, that comes up from Karma-Dejani's Minkowski normal numbers for continued. There's many others. Either way, you get that the set of continued fraction normal numbers is going to be pi03 complete by putting in alpha to be a continued fraction normal number and beta being something where the digits and blocks of digits follow some other sort of frequencies. And also note that this isn't going to be the case for all generic points for all measure-preserving systems. For example, if you're looking at irrational circle rotations, then the set of generic points is just the entire space, so it's Clopin. So there's something actually pretty necessary. I mean, we don't have an if and only if, but the specification property plays a very important role. Dominic and his student, Konrad Decca, and the follow-up paper we had that generalizes this more. This was just, maybe it was just published in ETDS, it was accepted, but it's, anyways, in ETDS either now or soon. They have, we got some examples. Well, they came up, I was a co-author, but they came up with these examples of other subshifts that have different complexities. So it's possible to get the set of generic points being pi02 complete, sigma02 complete, or even open or closed or whatever. So But these are cases where you don't have something like specification. So there's something very important about being able to do almost concatenations. And in terms of for you guys, look at this. Okay, this is some like problem we solved. We're doing concatenations, playing with digits, putting things together. This doesn't look like a set theory problem, right? So that's part of the point. This is part of the whole point of these lectures. One who knows nothing or very little about set theory can often come and be a very valuable contributing co-author on a paper that involves Borel hierarchy questions and whatever other area of math you're looking at by being very comfortable with the area that we're looking at. So that's one of the reasons I really wanted to do this sketch. So anyways, I think we can call it a day on that. So, thank you for having me here. I know it's been 6 lectures. Even then, it still feels rushed, but I'm glad to at least show this. So.